So welcome everybody to the OpenXLA Community Meeting. We usually kick these off just with a restatement of what OpenXLA is and what the project mission is as well. We're building an open state-of-the-art ML compiler ecosystem collaboratively with hardware and software communities, including the best of XLA, Erie, and MLIR. And generally in these monthly meetings, we invite new community members who are attending for the first time to introduce themselves, share their names and the organizations they're with, in any particular area that they're interested in collaborating around. So if we have anybody new to the community today, please speak up, or feel free also to drop a note in Zoom chat.
Okay, can everyone hear me?
Yes.
I can go first. I'm Praveen. I'm with Google, and one of the things that I work on is expanding our testing infrastructure.
Awesome. Thanks for joining, Praveen. And Praveen will also be presenting today, so thanks for signing up to do that. Anybody else?
Hi, I'm not quite new. I'm working for ARM and having a keen interest in OpenXLA, working well on ARM performance-wise and code generation-wise as well.
Awesome. Thank you for joining and welcome.
I'm Simon Waters, working for AMD. We are looking at adding native kernel generation support for our cloud GPUs.
Awesome. Welcome. Thanks for joining.
Yep. Thanks.
Anybody else? All right. And feel free also to drop a note in chat if that feels more comfortable for you as far as introductions. And I will move on. Let's see. Oops. Here's a reminder of the different organizations that are collaborating together in the OpenXLA community. And sorry, my slide forwarding is not going very quickly. Aha. So we also have a slide and resources around project collaboration for new members who want to understand how to join discussions in the community. And we meet monthly on Zoom on the third Tuesday at 8 a.m. So that's this meeting. We share our agenda a week in advance of the meeting on the OpenXLA Discuss mailing list, which is the best place to get updates on the OpenXLA project, including meetings and RFCs and technical discussions. And then we record and share meeting notes as well as the slides as soon as possible after the meeting happens. Here's the meeting notes doc in case you haven't already grabbed it. It should be linked through in the email that I sent out. I'm reminding people about the meeting, and that's a great place to add your own notes and also to sign up for upcoming presenting opportunities. So feel free to just drop in to this meeting note and propose topics for upcoming meetings. You can also email me at Thea, Thea @openxla.org in case you want to brainstorm about potential topics before officially signing up. All right, so we have a couple of active RFCs in the community right now, StableHLO TopK and StableHLO Extensibility, both of which we'll hear more about today. We also have a bunch of RFCs that recently closed and were accepted. Those are all accessible in the OpenXLA Discuss mailing list, and I can also link them in the notes later, but highly recommend that you take a look. I think we have stuff around MLIR HLO, StableHLO compatibility guarantees, GitHub organization management, and other stuff like that. So go ahead and take a look. And without any further pause, let's move on to Jakub's presentation on adding TopK op to StableHLO.
Okay, so my name is Jakub and I work on Erie primarily. And a couple of weeks ago, I posted an RFC for adding TopK to StableHLO. Next slide. So TopK is an op that is popular in transformer-based models and LLMs. The gist is that this is an operation that gives you like the top K values according to some criteria. So this can be something like, oh, what are the n largest values, or like what are the n smallest values in this tensor? And in addition to the elements with those like largest, smallest, or like whatever you define values, it also returns the indices of these values from the original tensor. And this is performance critical, or like this can be pathologically slow in some models, to the point where I think we went one slide back. Okay, thank you. To the point where I found some papers where they implemented hardware units just to accelerate TopK in their models. Next slide, please. And TopK is present in like the most popular ML frameworks and also IRs. So for example, like JAX, TensorFlow, PyTorch, and also like XLA, CHLO, MHLO, and Erie's Lineage X. It comes in a few different flavors. Like in some of these, like the values that are returned are sorted. Some of them they are not. Sometimes the K is dynamic, sometimes it's static. Next slide. So my proposal is to add a TopK op to StableHLO so that we can bridge this gap between existing IRs and our like IR dialects that we have, and also the ML frameworks. And the op looks something like this. It takes a bunch of values, and the K can be a constant, or it can be like a truly dynamic value. And it also takes an attribute that tells us whether we want the results to be ordered, unordered, or sorted. And it takes a region with some predicate that gives us that defines the ordering. Next slide. Yeah, I think it's one slide too far. Okay. And currently, the alternative is that whatever comes from the front end, we can lower it to some StableHLO. And a typical expansion right now that's sort of naive is to take the high level TopK, turn it into a sort, and then create two slices. One slice for the TopK values and the other slice for the TopK indices. So you can see that this is quite verbose. It's a lot of instructions. And not only that, this is not the only way to implement it. Next slide. So one alternative is to have a custom call, and then you can pattern match on the function name. And again, this can be expressed in multiple ways. And the issue with this expansion is that it loses this high-level information about whether the results were supposed to be ordered or not. So by having a new op for TopK, we would solve this problem of having to pattern match multiple different forms. Also, we would have like a concise canonical way to express it without losing this high-level information about ordering. Next slide. And one way sorry, no, this was one way to do it. And I planned some time for discussion about TopK, but this comes later because the next RFC by Kevin is related. And this would be like an alternative way to implement TopK, or like to introduce TopK to StableHLO. So we'll have time for discussion about TopK after Kevin's RFC.
Cool. Yeah, thank you. So I'm Kevin, also from Google. I work on the StableHLO team, and I'll be talking about the StableHLO Extensibility RFC. This is still in review. We're interested in any feedback, concerns, or use cases you may have for a feature like this. Please leave them on the doc that's linked in the bottom right of this slide. Next slide. So at the core of issues revolving around extensibility is that StableHLO doesn't provide a great way to capture arbitrary abstractions from framework to compiler. So in the example at the bottom here, we have a GELU operation defined in Python. This is largely a framework agnostic definition of it. And on the right, we can see the decomposition of, or that GELU function's representation in StableHLO. It's a bit lower level, and what we see is many consumers are doing some complicated pattern matching to try and reconstruct the higher level GELU abstraction. So pattern matching tends to be difficult. This is even one of the simpler examples of what people are pattern matching today. And one thing we currently do for some of these ops that can be decomposed into StableHLO is we put them in the CHLO dialect. But we feel that CHLO might be too high of a bar for experimentation. There's not really a good glide path to go from experimentation to figure out that an op design has some validity, and then to eventually make it into an op proposal to be added to either CHLO or StableHLO. So sort of trying to make a smoother glide path is another goal of this design. Next slide. So this RFC proposes a StableHLO composite op, which we liken to a function op with some structured metadata and the ability to version. So in the example on the bottom now, you can see there's a StableHLO.composite, and it has a string name, my.gelu, where my in this case is a vendor-specific unique identifier. It's basically something that a backend can match against. We have a version number in the attributes at the bottom of that example. Can we go back? There we go. We have a version number in the bottom of this example. This example here, a framework is directly targeting or directly generating the composite op. So as long as there's some way to attach the my.gelu, a framework would be able to generate this op, and this is a very easy and quick way to do some experimentation. If you look in the body of the op on the right, everything is representable in StableHLO, so you get all of the forward and backward compatibility guarantees that StableHLO has. Next slide. So another possibility is that you have an op in your dialect, my.gelu, and you want to provide a way to represent or express that op in StableHLO. So this RFC also proposes a extension op interface at the bottom, which has a method to decompose your op into a StableHLO composite op. It might be a hand up. I don't know if we take questions now or wait till the end. Why don't we wait until the end for questions, if that's okay?
Sorry, we can wait until the end, but I'll bring the question up then.
Okay. So next slide. So we have these StableHLO composite ops, and they are stored in portable artifacts with forward and backward compatibility. What does a consumer do with these? Well, in this case, if a consumer knows about this my.gelu, it follows the upward sloping arrow, and we provide another interface called Recompose, which allows a backend to take that abstraction and recompose it into the dialect specific op. And in this case, that would save them from doing some of this complicated pattern matching. But let's say a backend doesn't care about the my.gelu, they can just inline the body of it just as simply, and it's still agnostic to what the implementation was or what the name of this op was. It inlined it, and it's the same StableHLO we would have today. And next slide. So that part of it largely addresses the issue of not providing a way of capturing abstractions. The second half of this was the glide path for adding a new op to the op set. So we also propose a StableHLO extension dialect, which is a community supported composite dialect. As we sort of see what designs for composites are viable and winning designs, we can make proposals, the community can make proposals to add them to this centralized registry of composite operations. And the benefit of this is it's much easier for both producers and consumers to use these ops because they're shipped with StableHLO. So if you're already blinking against StableHLO, you can just start directly generating the extension ops. Next slide. And yeah, so as Jakub mentioned, we could represent TopK as a composite operation, and it has some benefits and drawbacks, and I'll hand it back to him to talk about that.
Okay, next slide, please. So here is like, if we adopt the extensibility RFC from Kevin and Eugene, one possibility for TopK is to have it as a composite op. So this would become an op in a StableHLO ext dialect that can be that can be expressed as a composite op, decomposed into a composite that preserves, you know, the name of the op, which is StableHLO ext TopK. And in the section with attributes, we can see that we can also preserve the information about ordering. So here, for example, the original op was unordered, and the backend config has ordering also as unordered to reflect that. But the implementation is still naive. So if nothing ever recomposes this composite, we'll end up with this kind of naive and slow expansion that depends on sorting. And you know, in addition to that, this form can be like, it's nice for serialization, like it can be version and so on, but it is still kind of very verbose, which is one of the drawbacks. Next slide, please. And here, I think it also shows one property of composite ops is that, like, the body of a composite op doesn't define the semantics. The semantics have to be defined, you know, by the dialect that introduces the op. So, for example, we could have a spec for StableHLO ext that defines exactly what TopK means, what the semantics and constraints are. But we cannot rely on the definition in the region for its semantics. So, for example, if we had an unordered TopK that's followed by a sort, and that gets expanded to the composite, and then, you know, it will end up with a situation where we have two sorts, but the presence, you know, of the sorts shouldn't allow the optimizer, you know, to conclude that, like, you know, one of the sorts is redundant. Because if we then take the composite and we turn it back into the StableHLO ext op, you know, it can be that you know, the second sort that follows it has to be present, because it's not guaranteed that the sorting will be performed internally. So in a sense, we have to be kind of careful here, because with this expansion, we have to treat the expansion, the decomposition, as a black box, and we can really depend on the definition after we inline. Before we inline, it's sort of similar to basically making an external function call. So coming back to, you know, to the idea of having TopK, I think that because of how popular it is, like both in models and also in other frameworks and IR dialects, I think this shows that it's kind of important enough that we should have it kind of in a dialect with a very clear specification. And I'll argue that TopK is kind of fundamental and important enough that it should be a kind of a freestanding op. And I think this is our last slide with Kevin, and I think now would be a good time for questions.
I can ask one particular question. Yeah. So with the composite op, it's a great idea, but the question is that, let's say I want to mark it from JAX. So there needs to be a hook, either a hook planned in JAX, so that I can basically say, hey, for this particular function, use this hook called StableHLO Ext my op, and then some other vendor could put a different hook for the same function. Rather than each vendor going in and creating their own copy of the JAX and adding those hooks to the source code. So we would need a hook as well, right?
Right. Yeah. So this design really focuses on what happens after the hook, and then frameworks can define their means for providing that hook independently.
So I guess my question was that, is JAX planning to provide this hook? Because if they don't provide a hook, then somebody has to make a copy of some piece of JAX and modify it for their distribution, right?
I would agree that it's important to align. They're aware of ongoing work for composites, but until we have a more solidified design, it's hard to start designing what the hook should look like.
Okay, I see. But okay, so in this particular case, example, still a vendor could take a hook and do something completely unrelated to what's in the body of the function, right? So it's not a very robust way, it seems, because what you're saying is that you are providing an alternative implementation, and this implementation may be, for example, in the same version of XLA, or where different vendors have to make sure that their hooks don't collide, right? They need convention, for example, vendor A say vendor A dot my hook, and vendor B dot my hook. They need to make sure that they never conflict if you have everything is open source.
Right. Yeah. So we need to make sure that the namespaces of what comes with, like the dialect, it's effectively a dialect, but we would need to make sure.
You need so that's another issue with this. I think that's the proposal that would need to be addressed at some point.
Okay.
Thanks.
Thanks, from chat, Jaya has asked, for the classic XLA GPU, it would be helpful to extend this design of composite op all the way to HLO as well, such that an analogous composite HLO op can be preserved, and that an HLO pass can detect and lower to a vendor-specific implementation. Any plans to extend this beyond StableHLO to XLA HLO?
It's certainly interesting, and would be interested to discuss that more. It sounds feasible. I mean, this provides a compiler backend a way to map an abstraction back to an operation. So it could be that XLA provides a way to preserve whatever that operation is on the compiler side. Or it could be that we keep this as an abstraction with a string with some metadata. Yeah, I think that would need a little more design, but it sounds very feasible.
Awesome. I'll note that for a follow-up. Any other questions?
To address one more question from chat, which was, do values flow or is it isolated? It's isolated, and yeah, exactly as you said, it's very similar to using a function. There's actually a hidden slide in this presentation which shows, and the RFC talks about a function being the alternate design, a function with a little bit of string metadata attached to it. The downside of that one was that you have to do additional work to prevent that function from being inlined from other passes or elsewhere in a compiler pipeline. Composite is more of a structured, it has attributes to it that you can expect, or that a consumer can expect to be there. But yes, this is very similar in behavior to what a function provides today.
Thanks, Kevin, and thanks, Uday, for bringing that question up. Any other questions? Okay, I think this would be a great time to move on to our next presentation from Praveen, where he'll be talking about some of the fuzzing work that he and the team are doing in XLA.
Thanks, Taya. So hi, everyone. I'm Praveen. Like I said, one of the things I work on is on expanding our testing infrastructure. And today I want to introduce an approach to randomized testing that we would soon be doing with OpenXLA, hopefully. Next slide, please. So at a very high level, I just wanted to motivate the problems that we're trying to tackle in general. So, our compilers are composed of, several program transformations. And as we incrementally build a compiler, our sort of interactions between these transformations can expose gaps in our unit tests. Like our initial unit tests might be targeted towards ideas of use cases that then evolve over time. And so sometimes unit tests tend to be not enough for us. On the other end, there are large integration end-to-end tests that are supposed to always work for our production compilers, and they can be time-consuming or resource heavy to run, and so we don't often run them for every change to the compiler, and so often changes that may break such tests don't get caught until some time has passed, so then it's harder to debug those kinds of breakages. And another motivation is, in general, when developing a new pass or a new optimization, we are often writing tests by hand. These are program transformations, so often tests involve inputs that are programs, and often our transformation might only sort of depend on some details of the program, but we're kind of forced to write all the details in order to provide valid input to the compiler. So that can be tedious. And in general, we would, we are writing these transformations that, keep some properties of our programs unchanged and vary other properties, or they may have assumptions about the input programs. And we would like to, stress test these properties and invariants that we expect. So these are generally the problems that, they may be familiar to everyone. But I just thought I'd lay them out as well. Next slide, please.
Oh, sorry. Oh,
sorry,
geez.
yeah, it's oh, wow. Okay. Great. Okay, so one approach, and this is certainly not the only solution to all the problems I mentioned, but one approach we're excited to pursue is just program generation, or randomized program generation, and see how much a tool like that can help us with these goals or other goals. So the main approach that I will describe today is about automatically generating valid programs. By valid, I mean type correct, and type correct means types in the sense of shapes and element types. And so we're sort of introducing a way to validly generate HLO, stable HLO programs, and we don't want to just generate arbitrary, random but valid programs. We want to guide the generators towards programs that actually matter to us. So one approach we're taking is sort of introducing a way to express program templates that are sketches, if you will, of an HLO or a StableHLO program, or at a higher level as well. And the holes that are left in the sketches are randomly, but are filled in a valid way. The idea is then we can use a generator like this to generate, thousands of programs or many examples and use them to test properties of the transformation. So next slide, please. So the approach I'm going to describe today is a tool that's it's a library in Python, and we call it XLA Smith. The tool is still a work in progress, but hopefully the ideas that I described today will open the floor for discussion. So in the tool itself can be used in there's like a spectrum of ways in which you can use it. The simplest way in which you can use the tool is simply to generate any random program without specifying any templates or anything. So here on in the screenshot of the Colab session here, we simply import the library XLA Smith and call the generator that's called random prog. And we simply say, give me one sample from the generator that's random prog, given some random state. And we convert that to HLO. Next slide, please. So when we invoke this call to the random prog generator once, since we asked for one sample, we expect some output like this. And here, since we kind of converted it to HLO program, we see HLO text. And we didn't specify anything about the program here. So sort of everything was randomly chosen for us. The shapes, the input shapes, the number of parameters. We have ops like transpose and reshape or convolution in this program. And they're all randomly chosen, but they're sort of valid in the sense that, the convolutions input arguments are given parameters that are valid. There are some baked in defaults to random prog, but we can start to have more control over the programs as well as we'll see soon. But before we get there, let's look at an example of how to generate multiple programs. So next slide, please. So here, we invoke not only the random prog generator, but a meta generator called n times that takes a generator and a number and invokes that generator multiple times. And so then one sample from this n times random prog generator, then gives us n samples or n invocations. So here too, we didn't actually specify anything about what the structure of the program that we want, but simply by invoking n times count, we get multiple programs. So this is just another example of how one can express random valid random programs. Next slide, please. Here, I wanted to just kind of go a little bit to the other end and show how we could start specifying templates of the program that we might want to generate. So consider that, consider the last line in the screenshot here. So in general, what we're doing here is we're defining some template called our rwconv_wise, and then we're using that template as our generator. So on the last line, instead of random prog, we're using this new generator that we have defined here. Next slide, please. So this generator is composed of building blocks like random prog and random type and choose. So here we're sort of asking for some random type that we will use as the output type of our program. Next slide, please. We're invoking two calls to random prog, each of which are, constraining the random subprogram in some ways. For example, by constraining the root of the program, or the size or the depth of the program, or which ops to exclude. Next slide, please. And we're using another sort of building block to choose from a set of ops that we might, are element-wise ops that we want as a final root of our program. And then finally, next slide, please, we use the element-wise op that we've chosen and the subprograms that we've generated to build up the final program. So if we go to the next slide, please, invoking this template once will start to generate programs of this structure, where the root op is some element-wise op from the set that we define, and the left-hand side is a reduced window, and the right-hand side is a convolution. But many of the other details are sort of chosen for us in a valid way, but random way. Next slide, please. And as before, we can invoke the meta n-time generator, which will now produce multiple samples from our custom sort of template. So now we start to get multiple programs, but they all have a similar structure of having an element-wise op the root and reduce window and convolutions as children. So this is basically sort of two examples of using library to generate sort of programs of a desired shape. And now we want to use a tool like this to in sort of testing our compilers, or in testing stress testing properties of our transformations. So next slide, please. So one thing we can sort of directly do is invoke XLA compiling on these generated programs. So at this point, like it's a good moment to for me to pause and mention that the tool is built on top of JAX. So even on the previous slides, we may have noticed there was an import of the JAX.lax library for expressing which ops we want to exclude or include in our programs. So the tool is simply based on top of JAX. It builds it works with the internal JAX representation called JAXPers. So a random program is a JAXPer. And so it also piggybacks off of PJRT to allow these random programs to be compiled using XLA. So we can, whatever backend we have access to, we can invoke that backend during compilation. So we can compile for GPU or CPU or TPU if you have that backend. So here's an example of simply calling one sample from the custom generator that we had written, and then sort of compiling, invoking the XLA GPU compiler. Next slide, please. Another high-level test we often want to do is execute our program against a certain backend and compare it to an evaluator and interpreter. And so again, as this tool is built on top of JAX, we can sort of quickly execute these programs as well. Next slide, please. There are other being on top of JAX also means you can do other transformations on your programs like gradient, or do other property-based testing depending on what properties you want to test. We did run some a handful of experiments with just generating random programs and running them through various backends. It was pretty easy to generate hundreds of programs that crash or fail, and they sort of map to roughly 20 different classes of bugs, and sort of you often see bugs or gaps basically in assumptions about optimization passes or even lower level passes like emitters. And sometimes failures are more not compiler crashes, but failures at runtime and during execution. You might often see failures, but that are sometimes not bugs. So, for example, if we're generating completely random programs and random inputs for these programs, you expect there to be infs or nans, and which are actually avoidable as well with a separate transformation that clamps inputs on every op. But then there are optimizations that actually, our compilers are composed of not necessarily numerics preserving optimizations. And so often, a change in numerics is not a bug. And so this is an interesting avenue for a tool like this. I think that there's some scope here for helping characterize the numerics behavior of our optimizations by sort of running sort of stress testing or optimizations across a wide distribution of inputs. Next slide, please. So one of the new things for OpenXLA specifically here is that we're starting to develop a regression suite. So this should be a suite of tests that we expect to pass for every change to OpenXLA. And the high-level goal is that we sort of want to generate and periodically enhance or update this regression suite automatically. So there are some initial tests in the directory on the slide here, and these tests were simply generated by calling random prog. They may or may not exhibit or express the most realistic use cases, but we already from developing a test suite like this, we already discovered some crashes that we were working to fix. But the sort of ongoing work is that we're developing coverage tools that we are then using to either prune the test suite to a smaller suite or enhance the test suite as well based on code coverage feedback. And there's going to be more work coming soon about extending the test suite with more realistic templates that should hopefully emulate a sort of realistic test, larger than unit tests, but smaller than end-to-end regression, end-to-end integration tests, but still that are small enough that can be run for every change to OpenXLA. And there's also work on automatically enhancing the test suite, not just via templates, but also through sort of mutation style, coverage guided fuzzing in the style of libfuzzer or EFF. Next slide, please. So please stay tuned for sort of an RFC for that specifies or details more of the design and implementation of this tool. And of course, it's ongoing work, so there are many more features in the pipeline. One of the features that we're excited about is sort of an explicit interface for generating StableHLO ops. So I mentioned that the tool generates HLO and StableHLO valid programs, and today that's sort of easy for us to do because we're sitting on top of JAX, and JAX is already natively lowering to StableHLO. But moving forward, it would one of the goals is to have an interface that is explicit about which dialect we want to generate programs in, and sort of closely following the semantics of the dialect that is expressed. And sitting on top of JAX.lax means there are many ops and attributes that we currently don't lower to that exist either in StableHLO or HLO. And so creating custom generators and lowerings is one of the items in our list. Please expect more features as well, like periodically generating new and randomized tests for OpenXLA, and going further and like improving the templating language as well. That's it for me, and I'm happy to take any questions if there are.
Thanks, Praveen. Does anyone have any questions? All right. And yeah, Praveen, we'll look forward to seeing the RFC you mentioned in the future. Speaking of RFCs, I did want to highlight one other RFC that is currently active in the community that I forgot to mention earlier, and that's the StableHLO quantization RFC. I've linked to it, I'll link to it in the notes as well. But we just had a great community meeting that Sandeep, the RFC author, led, I believe, a week or so ago, 2 weeks ago. And also the slides, or sorry, the notes of that community meeting can also be found in the notes today. So thank you, Sandeep, for leading that, if you happen to be here. Oh, good, we have another thing in chat. Okay, Oscar is mentioning MLF core, which could be a use case for this in the future, providing CPU and GPU deterministic machine learning templates. Thanks for sharing, Oscar. All right, if there are no other items, we may wrap a little early today. Let's see. Awesome. Okay, thanks everyone for joining. Our next community meeting will be on the 3rd week of July, and I think that that will be feasible given it threads through the different holidays in the summer pretty well. So please let me know if you're interested in presenting either an RFC or a quick tech talk for the next community meeting. This can be specific to the OpenXLA project, but we're also interested in hearing presentations about work being done in the broader OpenXLA ecosystem. And yeah, so just reach out to me or drop a proposal in the community meetings meeting notes doc, and looking forward to anybody else's presentations. So with that, I will conclude the meeting. Thanks again for joining, and we'll see you next month. And in the meantime, we'll see you on the OpenXLA Discuss mailing list. And thanks to our presenters.